Hey everyone, as a follow-up to our current series on a better understanding of the biofuels, biochemicals, and biomaterial narrative, this current presentation is going to explore the scaled up production of valuables using high moisture meat waste streams as a feedstock or as a renewable carbon source from which we can get these valuable products. Now, we're all probably aware of the current challenges associated with environmental resource depletion, environmental pollution, and global warming. In response to these challenges, this presentation explores the utilization of high moisture meat processing waste as a renewable carbon source that may be employed in the production of valuables of biochemicals, biofuels, and biomaterials. Now, during the course of this presentation, of course, the background of the study will be explored. Our motivation for this study will be discussed. The methodologies we have explored so far will be discussed. Results, justification of the present work, and of course, conclusions will also be presented. Now, generally speaking, based on the case study of New Zealand, you have a significant amount of this waste stream generated annually, given that New Zealand is a major meat processing exporting country, So in other words, you have a lot of waste streams that are associated with the production of meat products, Of course, these waste streams are high in concentration of carbon waste compounds, carbohydrates, proteins, lipids, which can be valuable resources or carbon sources for the production of these biochemicals, biofuels, and biomaterials. Now, generally speaking, this particular waste stream is characterized by significant issues associated with the management of the waste stream. Now, this is because typically these waste streams are high in moisture, implying that you cannot simply just dispose them in landfills, which is also not a particularly environmentally favorable approach for managing organic waste. Of course, you also have the issue of smells, because due to the possible microbial degradation that occurs in such high moisture scenarios, you have unpleasant smells that also limits the ability to dispose these wastes directly into the environment. Of course, we're also trying to see the possibility of exploring the circular economy, in other words, finding ways to recover valuables from perceived wastes and organic streams. Now, of course, we must also acknowledge that beyond this meat processing wastes feedstock, virtually every high moisture organic waste feedstock can employ similar technologies that will be discussed in this presentation. In other words, we could use the same technologies in managing municipal sewage. Now, what's the basis of this research, In other words, we have assumed that it is possible, for us to recover valuable products, from high moisture waste streams, while circumventing the need for introducing a high energy intensive preliminary drying operation. In other words, we have found a way to integrate an in situ or one pot process that negates the need for this drying operation, because this is identified as a major limitation for converting these organic waste streams to solid fuels. Now, this methodology will be discussed during the course of this presentation. Of course, if we can find a way to recover valuables from a perceived waste stream, clearly there will be benefits to that, because now, rather than having a waste that you need to dispose of, you have a waste stream that is actually considered valuable, since it's a feedstock to a process that facilitates the production of a higher value product. Now, it is our hypothesis that if we can have a system that can present multiple streams of high value products, you have the opportunity to have a scenario where the productivity, the economic feasibilities are higher, rather than having a target product system. In other words, if we had a system that could produce biodiesel, biogas, biochar, biocrude integrated into one system, or in this case, biorefinery, by the integration of different biomass conversion technologies, there is a chance that the economic performance of such an integrated system will perform way better than when it's just isolated to target a single valuable product. Of course, such a unified approach that facilitates the production of valuables via the integration of biomass conversion technologies more or less describes the biorefinery concept. Now, during this presentation, during the course of this research rather, we have integrated technologies that facilitated the production of biodiesel, biomethane, right, biocrude and biochar. Now, biodiesel essentially employed the utilization of a stepwise production system that integrated a one-pot in situ hydrolysis for the conversion of available lipids in the meat processing waste stream to fatty acids, prior to the esterification of such fatty acids to biodiesel under the action of an appropriate alcohol. Right? Now, the residue of this biodiesel production process is actually rich in carbohydrates and proteins, and of course still has a significant amount of moisture content, suggesting that we can actually use that feed stream by the integration of another waste stream, in this case stockyard waste, which is where the stockyard where animals are kept. So it's a mixture of their feces, their organic wastes, their wash-offs, right, and their spills, their feed spills, right. So utilizing that as a co-substrate, we are able to enhance the production of biomethane by the introduction of certain synergizing effects that have been described or demonstrated experimentally during our experimental studies. Now, finally, we have integrated a process called the hydrothermal liquefaction process, which is a process that imposes super or subcritical conditions on a reaction medium, such that you are able to the system is able to undergo depolarization, condensation, and indeed polymerization reactions to facilitate production of a high energy dense product, in this case biocrude, which is, from our level, we can consider it as being analogous to the fossil crude. In other words, it is a product that is composed of high value biochemicals within the mix, right? It's also energy dense, can be as high as 40 megajoules per kg, per kilograms, right? And for all intents and purposes, can be upgraded further by undertaking hydrogenation reactions to reduce the oxygen contents or the oxygenated compounds present within the mixture. And of course, biochar is also produced, which can be utilized in this case as an agricultural soil additive to enhance the soil properties in terms of porosity, reduction of acidity, and of course as a useful source of trace minerals. Right? Now, figure 1 more or less highlights outputs generated from this study that can be read. The links are also presented below so that we can go have a quick look at this experimental results that were obtained and published and for online online journals, right? So you have the opportunity to go read more based on the outputs that are presented here, right? So I'll present the links down below for our benefits. Now, figure 1 essentially summarizes the integrated system I was talking about. You have a meat processing plant that produces high moisture with waste stream, or DAF sludge in this case, dissolved air flotation sludge, right? Which could be anything, any organic waste stream that is high moisture. In other words, you could easily replace that with municipal sewage, right? Wastewater, right? So essentially, high moisture streams could also serve in there, right? Now, this DAF sludge is subjected to an in situ hydrolysis process, which is just fancy for a one-pot hydrolysis process that facilitates the hydrolysis of the lipids, right, within the reactor, such that you can easily recover the fatty acids, which are then subjected to an esterification reaction for biodiesel production. Of course, this is catalyzed. In our case, we have utilized the Dowex reactant, Dowex catalyst in this case, because the Dowex catalyst is heterogeneous but also quasi-homogeneous. In other words, it has the capacity to rapidly release hydrogen ions that can help to catalyze the hydrolysis reaction for the lipids, right? Now this will be available in a publication that I've provided in the link that tells you the reaction steps that typically occur within this in situ hydrolysis reaction, right? Now, as I said earlier on, you still have a lot of macromolecules that are present in the residue. In this case, glycerol, hydrolyzed carbohydrates, proteins, and others. You have amino acids, so different levels of hydrolysis products, are present within the residue. Now, of course, these residues can be a high or beautiful source of organics that can be further degraded to produce biogas, right? However, to enhance the biogas yields, right? Biogas is essentially a combination of biomethane and CO2, right? Largely, right? Now, to enhance the yield of this biogas product, we had to introduce another organic stream called the stockyard waste that introduced certain synergizing effects. So you had these synergizing effects that, for instance, reduced possible limiting effects of the Dowex, right? Of the Dowex catalyst, right? You understand? So the possible acidic effects of having some short chain fatty acids that may not have been recovered via the in situ hydrolysis process, right? So this stockyard waste facilitates the neutralization of the negative effects that may occur by utilizing the hydrolysis products from the in situ hydrolysis reaction, right? Now, of course, after the anaerobic digestion process, you have your biogas obtained. You have the opportunity to upgrade this biogas. There are so many methods to do this, right? One easy way would just be to bubble the biogas through an alkali, right? So that the CO2 gas is dissolved and reacts to form the carbonates, right? Leaving your methane, almost pure methane, available for use as a cheap fuel, right? However, you still have your digestate that is generated post the anaerobic digestion process. Now, this digestate may be employed as a feedstock in the hydrothermal liquefaction process to produce a biocrude, the biochar, and a post-hydrothermal liquefaction water. The gaseous products are essentially largely CO2 gas, with an experimental assessment and result of the gaseous product was established that it's almost 90% CO2, right? In terms of composition, so it's really not useful, right? But of course, the biocrude can be used directly as a fuel, right? Because of the higher heating value, right? And of course, it could also be further upgraded to reduce the amount of oxygenated compounds within it, right? Making it more useful as a direct feed to a refinery. So in other words, you could consider it as a low-grade fossil crude, right? With the major issue being that it contains some concentration of oxygenated compounds within it, right? This needs to be reduced. Right? Of course, upgrading is another level of cost that involves some form of hydrogenation reactions, right? So as I said earlier on, the papers here, the links are going to be presented below, so we can go have further reads so we can better understand the process, right? Now, having undergone the experimental study, right, now we propose the biorefinery model. This is a very simple biorefinery model that shows the biodiesel production process, which we have specified as step 1, right? The anaerobic digestion process, which we have specified as step 2, and the hydrothermal liquefaction process, which we have specified as step 3. Now, based on this model, we try to make sure that there is some agreement between the yields generated from this scaled up biorefinery model and what we obtained experimentally, right? So that there's some form of some basis for comparison, right? So there should be some correlation, right, between what we are saying we can get from the model and what we are getting in the labs, right? Now, essentially, to assess the biorefinery model, we have investigated both the economics, right, and the environmental performance. Now, for simplicity, we have utilized the net energy ratio, right, which tells us the amount of renewable energy as represented in this case by the fuels that we get, the fuel streams that we get, the biofuel streams that we get, relative to the energies that we have to feed into the system, to generate the product, right? So the fossil-based energy fed in, you get, and the energy we get out of the system, right? Now, generally speaking, an NER value, a net energy ratio value, greater than 1 is considered ideal. Right now, we also considered the economic performance in terms of the unit production cost. So we considered the unit production costs, the capital costs of the plants, the operating cost of the plants, the energetics of the plants, considering the possibility of heat integration and heat recovery, right? So we considered all these factors and we try to optimize the system. So typically optimization in the simple terms is just to find the conditions that enhance the particular target product, right? In this case, it was multi-objective optimization, implying that we had to optimize 2 major equations such that there was an accepted trade-off. You understand? Now you have a scenario where you have objective functions that you need to simultaneously optimize, right? So you have to have a trade-off. You cannot have, there has to be a trade-off between both objective functions, right? Now, to achieve this, we have utilized genetic evolution algorithms in this particular study. Of course, this can also be done using the desirability function approach, which is available in most statistical software, right? Now, what is the result of this study? Now, we try to compare the unit production cost of the products, the target products of char, biocrude, biodiesel, and biogas with what we obtained from peer-reviewed literature, right? And indeed, we were able to establish that, with the exception of the biogas suite, there was no significant difference in the unit cost per unit volume, because this was very, very almost inconsequential, right? But we were able to observe some benefits of integrating the biomass conversion technology to simultaneously produce the target products of diesel, biochar, and biocrude, right? So of course, we had scenarios where we assumed that the energy supply to the system was obtained from renewable energy sources, as in the case in New Zealand, where most of the energy generated is obtained from renewable energy sources. We also try to provide a comparative assessment, assuming all the energy required were from fossil resources, right? Just to provide the basis for said comparison. Excuse me. Right. So we can see that indeed there's a possibility that integrating this biomass conversion technology is actually better, right? In a large scale, right? With the exception of biogas, of course. Now, what was the conclusion of this study? Of course, we were able to demonstrate that yes, it is possible. Experimentally, we can utilize meat processing waste to produce the target products of biodiesel, biochar, biocrude, right, and biogas, right? So this is possible, right? Now, of course, utilizing meat processing waste as a feedstock, or indeed any other high moisture waste stream, right, provides an opportunity, provides a very good opportunity for in production of these biochemicals and biofuels, high value biochemicals and biofuels, via introduction of valorization technologies, right? So there's potential in this, right? There's potential in this, especially in Africa where we have a lot of organic waste streams. There is a potential for us to utilize high moisture waste streams by the integration of biomass conversion technologies to achieve the production of alternatives to fossil-based products, right? However, we understand that the high cost of such an endeavor may indeed deter investors because it's actually not a cheap enterprise, right? Of course, there are also technical risks associated with upscaling such complex biorefinery systems. And of course, if we have a scenario where we have low crude oil prices, it will be difficult for us to propose or encourage the utilization of alternative biocrude, right? Because at the end of the day, people are trying to make money, right? However, we cannot negate that in the long term, you have an opportunity to produce a biocrude product that, for all intents and purposes, is a high energy dense product that could be utilized as a fuel, right? It has comparable physical properties to crude oil, right? With the greatest limitation being that it also contains oxygenated compounds. Of course, these oxygenated compounds can be removed while undergoing another stage of upgrading that, again, as I said earlier, just involves some form of hydrogenation, right? So this is doable, right? Now, I want to thank you for listening, right? Now, understanding the technical basis of this research, I have, as I said earlier, provided links that can be available for further information. So I will encourage us to go read more, right? The future is renewable, the future is biofuels, the future is organic waste. Thank you.